going on? My name is Andrew Cole.
I'm Thomas Deguire.
I'm Brendan Fox. This is our Lab 4 Tensile DIC presentation. The objectives of the lab are to become familiar with DIC software and use the software to determine lateral and axial displacement data, and to take that data and determine the transverse and axial strain of three different specimens, copper, aluminum, and polymer. And we are going to use that data to calculate Poisson's ratio. The theory behind the lab is that Poisson's ratio can be calculated using lateral and axial strain. You take the lateral strain and axial strain, you divide it and multiply it by -1, as seen below in equation 1. Poisson's ratio is important in engineering, and especially material choice and characterization, because when making designs, the lateral strain will be affected by the axial strain on a material or a part. A good example is in plumbing and piping. The flow of a fluid through a pipe can increase the pipe's lateral strain, and therefore it can affect the axial strain, and the pipe might fail due to that. And those are the things to take into account when you're designing pipes and some sort of piping system, something like that.
Looking at the equipment and materials we used a copper, aluminum, polymer, dog bone tensile specimen. We had a force gauge, displacement dial, clamps to hold our test specimens, and a gauge caliper. The methodology was to ensure that the speckle side of the samples was facing the camera to allow for data points to be collected. We measured the gauge length, the width, and thickness of these samples, performed tensile tests on each, and record using a camera in the GOMS Snap software. We analyzed the lateral and axial displacements of these samples in the GOMS software, calculating lateral and axial strain, which also allowed us to calculate Poisson's ratio.
This is our collected data for a polymer sample. So figure 1 of here shows the plot of the axial strain versus time, and figure 2 shows the transverse strain versus time. So looking at these graphs, you can see both of them have a linear slope, roughly, with the transverse one being negative, which makes sense as the transverse means the width is decreasing. You can also see that transverse strain is a major dip there towards the end, but it returns back to that linear path after that. Right here is the aluminum sample data collected in the same way as the previous one. This also shows a linear path, a linear connection between both of the strains and the time. You can see though in both of the plots towards the second half of the graph, things seem to flatten out a little bit. And right here is the collected data for our copper sample. So again, showing that linear pathway, but for both plots, it seems to start off pretty steep, but gets a little bit flatter towards the end.
Looking at our polymer test subject, we found 2 points of axial strain and transverse strain put into the Poisson ratio equation. And then we compared that to accepted ratio, and we found a percent error of 9.16%. Using a similar process for aluminum, we got an axial strain of 2.9 and transverse strain of -1.9, and used that to find Poisson's ratio, and accepted ratio of 0.35, and our percent error is 89%. And again with copper, we had a Poisson ratio of 1.28 and the accepted 0.355, which we found a percentage of 276%, which shows that the GOM software might not be as accurate as we hoped for.
And just to conclude, so the results of our experiment showed that one of our trials was successful. We yielded a 9.16% error, which was very good. It's under that 10% acceptable. But for our other two, we received very, very high percent errors. So it shows that the lab theory, that lateral and axial strain is directly related to the Poisson's ratio, which we found in the polymer experiment. But the large percent errors are suspected to be for a software error and issues using the GOM correlate software. So using this, we found a little gray area in finding out if it's an accurate way to find Poisson's ratio versus doing a manual tensile test and collecting data in that way.
For future work recommendations, as we glossed over in the conclusion, GOM correlate seems to be a little inaccurate and finicky sometimes when it comes to scaling the imaging, and it can be a bit of a complicated process that can be a little bit confusing. So we recommend maybe trying to use software that is a little more user-friendly and easier to use. Future research areas can include research into the Poisson's ratio of engineering materials, as mentioned earlier. The plumbing example with the pipes, a real-world application like that is a great field of research to go into. That's all for our presentation. Thank you for your time.